All right, couple things before we get started today. First of all, the school has added 2 additional sections of this class. Previously there was just lab on Tuesday and Wednesday, but they have since added a Monday lab. So there are now 6 options for lab. And because of those additional registration options, there might be some new people in the room, in which case, if you are new, welcome. I'm Josh Hoffbauer, and I am the lecturer for Phys1000, and it is nice to meet you. If any new students have joined, we need to make sure that you are in the course Brightspace page. I'm in the process of adding everyone that I've noticed that I know has joined since the announcement. But just to confirm what you should be seeing when you're added, once the basement Wi-Fi decides to work. To make sure that you are in the Brightspace page for this course, you want to see Hoffbauer, the Physics of How Things Work, Spring 24. And if you need information about the course, that is contained within the Introductions and Resources tab, which includes the syllabus. The syllabus has all the information you would need about the course, including the link to the YouTube channel where I post the recordings of all of my lectures. So if you have joined and didn't attend on Monday or Wednesday, you can catch up on what you missed there. Now, and this is now an announcement for everyone, whether you joined recently or not, since there is now Monday sections to the lab, I have to adjust my schedule slightly because class isn't open next Monday. And that means that I'm actually canceling lab for the whole week, because what I don't want to happen is Tuesday and Wednesday meet and they be ahead of the Monday crowd. I need every day of the week to be the same lab. So, across the board, no lab next week at all. So lab might be a little bit behind what we're talking about in the lecture itself as a result of that, but I'll make it work over the course of the semester. So, official announcement, no lab at all next week. Additionally, no lecture at all next week. So I won't see you next Monday. If you show up to this room next Monday, I won't be here. Any questions about any of that information or anything else that's on your minds before we start on physics today? All right. In that case, let us resume where we left off last time. On Wednesday, we began talking about the scientific method, the steps that are required to do science, and that does include physics. Within physics, our favorite part of the scientific method is the data section, because data is as close to truth and fact as we are objectively able to measure. And so for this class, we are going to need data. And so we have to talk about the data we're going to use, how we measure it, the units we use, and the math that we do with that data. So we are now entering basically algebra boot camp before we get started with the rest of the course. In order to measure something, you have to decide what unit you're going to measure it in, and physics likes to use the metric system for its units. This means instead of feet and miles and pounds, we are going to be using meters and newtons and all sorts of similar things. Who has never used the metric system before? Just to check. Okay, good. That's really. So these currently on the screen are some very common metric units, just to get them back into your brain. For distance and displacement, we like units of meters. The imperial, whenever I give you a new unit, I'll try to mention the imperial/American counterpart where there is one. So the counterpart to meters is things like feet and inches and miles. It's just a unit of distance. For velocity, we like meters per second, m/s. This is the counterpart to things like miles per hour. For acceleration, we like meters per second squared. There's not a common imperial unit to acceleration. It's not something that comes up much in Common English in my experience. Force, we measure in newtons, named for the scientist Newton. The imperial counterpart to that is pounds. So wherever you would use pounds in your normal life, we are going to be using newtons instead. 1 Newton is about, nope, sorry, rewind that. 1 pound is about 4.4 newtons. So whatever you weigh in pounds, multiply that by 4.4, and you get your weight in newtons instead. For a sense of scale, I, fairly average adult human male, weigh 1,000 newtons, just to help with your scale. For mass, we like kilograms. This is kind of a weird exception because normally physics likes to use base units without any metric prefixes, except for this one. We like kilograms instead of grams. All the formulas I give you and all the constants used in that formula assume you are plugging in kilograms instead of grams. Now, if you take chemistry courses and bio courses, they tend to use grams, and that's because those disciplines tend to work with small amounts of materials at a time usually. If you've taken a chem lab before, usually you're working with a teeny tiny pile of dust that you pour into a teeny tiny pile of liquid. And so those subjects tend to use grams for that reason. But in physics, we tend to be working with things like people and cars and planets. So we use kilograms, which is a bigger unit, to make the numbers smaller. Does that make sense? The bigger the unit, the smaller the number. So we use kilograms in this class. That's going to be our base unit for mass as we start measuring mass and calculating things based on it. And there isn't really an imperial unit for mass that we commonly use in the United States. Time, we like seconds. Minutes and hours exist, and you'll commonly have to convert minutes and hours back into seconds. All of our formulas are going to assume seconds, unless otherwise indicated. Now, you've been dealing with units, and you can use, like in your common life, loads of units exist. Like for example, you could be told the distance between here and somewhere else in miles, but for this class, we're going to have to be able to convert it into the metric system. So, to talk about metric conversions, the first thing we have to remind ourselves of is the metric prefixes. The ones boxed in red are the most common ones that you should be familiar with, the ones that you'll have to use most often. But for completeness sake, this table has every currently available metric prefix. The blue line represents a base unmodified unit, and then every prefix above that line makes the unit bigger. Every prefix below that line makes that unit smaller. So if we're using meters, for example, blue line would represent one base bog standard meter, which if you don't use meters very often, for scale. This is a 2 meter stick, by the way. This is not 1 meter, this is 2 meters. So from the end to my hand is 1 meter, about 3.3 feet, slightly longer than a yard. So that is one base bog standard out of the box meter. Now, we don't want to have to measure things like the distance between cities in meters because the numbers would get pretty big. So instead, you add prefixes above the line to make the single meter bigger. Deca is 10 times bigger, hecto is 100, and kilo is 1,000. We like kilo in physics, it's very commonly used. If you need to make a unit smaller, you go down. Deci is 1/10 as big, centi is 1/100th. Centi is the same root word as in cents and century, means 100. And milli is 1,000 times smaller. So on a standard meter stick, 1 decimeter is 1/10 this size, 1 centimeter is 1/100th, and 1 millimeter is 1/1000th. As I said, the ones in red are the ones you're going to have to use most often. The prefixes get pretty extreme though. I might occasionally use, mega or giga if I'm just trying to emphasize how big something is. I'd say in terms of the smaller ones, the only one that might come up occasionally is micro. But as long as you're comfortable with the ones in the red box, you should be fine. Yes?
What are some examples of things that we measured with micro, nano, and
I would say micro comes up most often in my experience when you're doing electricity. Microfarads is a pretty common unit for capacitance. But in terms of more common places to see micro, I'm having a hard time remembering right now. I don't use it much in this course. I just try to avoid it because it's not one of the ones that people have memorized. Yeah, off the top of my head, I'm struggling to remember something other than microfarads. Sorry. That said, this is the way my brain works. I believed on Wednesday you asked about the time dilation for things moving around quickly in orbit. That is 1/10,000th of a second slower per 6 months. So it's not hardly noticeable except for very precise clocks. But we've measured it, it exists, it's just, you might not notice it otherwise. I suppose, oh, you know what, that would be a microsecond. So I'll tie it into that. There's 1 microsecond difference for every 6 months you spend in orbit. And that's because you are moving very fast in orbit. It's not because you're in space, it's because you have to move quickly to orbit the planet. So that's an example of speed affecting time. That's not on the syllabus. I just like talking about space. The red box ones, if you've used them before, you're probably familiar with the acronym Kilo, Hecta, Deca, Base, ECM. King Henry died by drinking chocolate milk. Does that sound unfamiliar? Okay, good. Oh, someone was nodding. King Henry died by drinking chocolate milk is just a common acronym or euphemism, I don't know, for remembering the order in which these things go. You're more than welcome to write this on the top of your formula sheet. Like some students just like to use the visual leapfrog method of converting units, which is fine. You can write that on your formula sheet and it will be fine. Those are the ones that you're going to have to use most often, and so those are the ones that we are about to practice. Any questions before that? All right. So on screen right now are some pretty common types of metric prefix conversions that we're going to have to do in this course. And I'm going to give it to you guys to practice them briefly on your own or with each other before I go over the answers. First up, we're going to convert 10 meters into kilometers, 100 centigrams into kilograms, 1,000 kiloliters into milliliters, 25 kilometers into meters, and 0.25 kilograms into grams. So look over these for a second, using your calculator and just practice converting these for a minute, and then I'll go over what the answers are. Bless you. Bless you. All right. So, how many kilometers are 10 meters? 0.01. Very good. Now, I've been doing this for a while. I know to just, if you're going from meters to, from base to kilo, you want to divide by 1,000. That's because kilo is 1,000 times bigger than base. If you're going to a bigger unit, the answer should get smaller. Now, some people like the visual method, so I'm going to demonstrate that. I'm going to write out the number 10, note where the decimal point is in the number 10, and to do the visual leapfrog trick, if you write out King Henry died by drinking chocolate milk, look at where you begin, and then you want to leapfrog your decimal point a certain number of times to the left or right to get it from where it starts to where you want it. So going visually from base to kilo, you need to take your decimal point 1, 2, 3 places to the left. 1, 2, 3. So that will be 0.01 kilometers. Again, bigger unit, smaller number. Feel good? All right, how about 100 centigrams to kilograms? How many spaces is that? It's actually 5. Centi is here. So 1, 2, 3, 4, 5. So centi is 10,000 times smaller than kilo. 1, 2, 3, 4, 5. 0.001 kilograms. 100 centigrams is not a lot, so it makes sense that that would be a really teeny tiny amount of kilograms. For a sense of scale, I find people don't use grams a whole lot. They usually keep a 1 kilogram chunk of metal in here, but it's not in the room at the moment. 1 kilogram, I'd say, is about 2 of my filled up metal water bottle. 1 centigram, you probably wouldn't notice the mass up, if I'm being honest. 1 gram is like a paper clip, so 1 centigram is 1/100th of a paper clip. So you probably wouldn't notice this much mass. How about kiloliters to milliliters? We're at 1,000 kiloliters. How many milliliters is that? Yes?
Million.
I think it's actually 1 billion. Because this one's interesting because it's going in the opposite direction. We're starting with a big unit and going to a smaller one. So to go from killi to base, you'd actually multiply by 1,000, and then base to milli, you'd multiply by 1,000 again. 1, 2, 3, 4, 5, 6 decimal place hops to the right. So the decimal point starts there. 1, 2, 3, 4, 5, 6. So that's 6 extra zeros tacked on. So that is going to be 1,000, million, billion, 1 trillion, actually. No, I take that back. I got my words messed up there. I apologize. That's 1,000. It's a billion. It's a billion. I apologize. But it's 9 zeros total. Any questions or issues there? I realize I misspoke a second there. All right. How about 25 kilometers? How many meters is that? A little louder. I heard someone say it.
25,000.
25,000. Perfect. Kilometers are 1,000 times bigger. So the number we'll get 1,000 times bigger. Note again, kilo is 3 decimal points away, and since we are going from the bigger unit to the smaller one, drag the decimal point to the right. That makes the number bigger. So 25 with 3 extra zeros is 25,000. And then 0.25 kilograms, how many grams is that?
250.
250, very good. So same number of skips actually, because we're going from kilo to base. 1, 2, 3, so 250 grams. As I mentioned, we'll talk more about mass and how we're going to use it later on. We're just kind of doing the conversion part of the units right now. We like kilograms in this class. Physics just bases all of its formulas around kilograms instead of grams. So pretty often you're going to have to especially convert grams into kilograms before you can use them in any of our formulas. So out of all of these, this one is, well, I guess going in the reverse order would actually be more common. So I'd say number 2 would probably be the one to keep in mind. We like kilograms in here. You're gonna have to get things into kilograms pretty frequently. How do you guys feel right now? All right. Now, metric prefix conversions are not the only type that we're going to have to do in this class, and that is because there are loads of units of measure that aren't metric that we have to convert into metric. I misplaced my erasers a lot. So, we also need to practice non-metric prefix conversions, things like turning feet into meters, hours into seconds, and things like that. And I especially want to practice this because I'm going to be the one writing on the board, and I want you guys to be familiar with how I do these, because I have a specific tactic for doing conversions. Some students like it, some students don't, which is fair. You don't have to use the same method I use for conversions, but I want you to be familiar with it because you're going to be seeing it a lot in this class. So, we're going to practice conversions and make sure that, if nothing else, you've at least seen how I do it. So, first up, this is going to be a fairly standard sort of conversion. We need, for time measurements, we love seconds in physics. Seconds is the base unit for time that we like to use. So if you're ever given time in a unit that isn't seconds, you're usually going to have to convert it into seconds. So, to start with, how many seconds are in one day? Now, to do any conversion, you usually need a conversion factor. So going from seconds to the units bigger than it, how many seconds are in 1 minute? Very good. Not a trick, I promise. Whoops. Also not a trick. How many minutes are in an hour? Very good. And once again, also not a trick. How many hours are in one day? 24. Thank you. So, just for completeness sake, I have written these conversion factors on the board. A conversion factor is just an equivalency that tells you how much of one thing equals another thing. These two things are equal. They mean the same thing, they just use a different unit to describe it. Additional quirk about myself, if a 1 is by itself, I usually write it like this to make it clear that it's a number 1. Now, the way that I use these, like any conversion factors, even ones that aren't as common as these, the way that I use them if I want to visually show that I'm converting something is I use what's called the railroad method, or sometimes the fence post method. Now, within this question, we are tasked with finding the seconds in one day. So our starting unit here, our starting value is 1 day. And I begin by writing out that starting amount. We have 1 day, we need to convert that 1 day into something else. And the way that I visually do conversions when I'm physically writing my workout is I take that initial value and I start multiplying it by a bunch of fractions to cancel out the unit I don't want and replace it with the unit I do want. Looking at these conversions here, we've got 24 hours equals 1 day. These two things are the same. They mean the same thing. This is an equivalency. The equal sign means same thing. Bless you. Now, to get in a little bit of the algebra that we're going to be using later, since if we treat this like an equation, 24 times hours equals 1 times days. If we treat this like an equation, I could move things from one side of the equation to the other. And so if I wanted to, if I could say subtract 1 day from the right to the left, and I get 24 hours minus 1 day equals 0, which makes sense. That'd be something minus itself equals nothing. But I could also divide both sides by 1 day. So what I'm going to do is 24 hours equals 1 day. I'm going to divide both sides of this equation, by 1 day. Now on the left, we now have a fraction, and on the right, we have something divided by itself. And when you divide something by itself, what happens? It just becomes 1. 1 over 1 is 1, 2 over 2 is 1. Anything divided by itself is just 1. So, the fraction 24 hours divided by 1 day is therefore equal to 1, which makes sense because 24 hours is 1 day. This is also still dividing something by itself, right? So this is our proof that 24 hours over 1 day equals 1. And if this fraction equals 1, what happens when you multiply 1 by anything? Same thing. It doesn't change its value at all, right? 5 times 1 is 1, 6 times 1 is, 5 times 1 is 5, 6 times 1 is 6. Multiplying something by 1 does not change its value. And since this fraction is equal to 1, I can multiply anything in the universe I want by this fraction, and I don't change its value, right? All that preamble is just getting to me taking this fraction and writing it here. "24 hours over 1 day. That fraction is equal to 1, and I am multiplying that fraction times my original value. Since the fraction is 1, I am not changing the value of 1 day, but I am going to take advantage of the fact that technically I now have days divided by days. If you consider the unit to be part of the equation, units can cancel like how numbers can. So right now, if I was just looking at this fraction, trying to solve it all the way out, this is 1 day times 24 hours divided by 1 days. 1 day over 1 day cancels. And if I perform this operation, this would convert 1 day into 24 hours. And so what I show next when I'm writing these sorts of things out is I physically cross out the units that cancel out, showing that now after this operation, I'm just left with the number of hours that are equivalent to my original unit. I know that was a lot of preamble. Again, I want to make sure that my method here makes sense here at the beginning of the course before I start using it all over the place. How does this feel so far? You do not have to use this tactic in your own work. Just want to make sure that when I do it on the board, it makes sense. All right? Now, this is just turning days into hours, which, you know, you guys could probably already do. We already wrote out that equivalency. But in the case of longer conversions, I can add more fence posts or more links to the railroad track. This is kind of where the term fence post or railroad comes from. It's just fraction by fraction by fraction. And I can just add more links to keep transforming units as I see fit. The next link is going to be turning hours into minutes. 60 minutes is 1 hour. Again, I can turn that into a fraction that equals 1. And since I want to cancel out hours, I need to make sure that the hours part is on the bottom and the minutes part is on the top. If you are using this method, you need to make sure that the unit you want to get rid of is put in the right position to cancel out with its counterpart so that you are left with the unit you want. So I'm taking this equivalency, turning it into this fraction, and plugging it in such a way that this hours cancels out the hours I already had, and I'm going to leave it with minutes in the numerator instead. And then I can go one step further and do the same thing with minutes to seconds. And after all of those fence post links, all those railroad tracks, the analogy is breaking down. I now have one long, complicated thing that I can put into my calculator, strung together to get to the final answer that I want, to get to the number of seconds that were in my original 1 day. So that's my method that I use when I'm writing out my work. If you like this method, or ever need to follow along in my work, I would then take this long chain of things and put it into my calculator. And if you haven't used a scientific calculator in a minute, I'll write out how I would put, like what buttons I would type, what you want to see on the screen. 1, open parentheses, 24 over 1, close parentheses, open parentheses, 60 over 1, close parentheses, open parentheses again, 60 over 1, close parentheses. So if you type that string into your calculator, it'd be the same as 1 times 24 times 60 times 60, because the dividing by 1 doesn't do anything. So you get the same result if it was just 1 by 24 by 60 by 60. And that will tell us the number of seconds in 1 day. It's 86,400. That was a lot of work for one conversion, I admit. But at least as a tactic that you will be seeing on the board, how does that feel? All right. If the way that I do this doesn't make sense at any point in time, I want to know it. If my conversions ever trip anyone up, I want you to tell me in general.
any questions, any issues at any time, interrupt me. I want to know so that you can understand that the next thing isn't confusing, building off of the confusing thing. Got a couple more conversions here that we'll practice, and again, I'll use my method just to try to enforce how it makes sense, or try to make sure it makes sense. Any issues if I erase this before I move on? All right. All right, next up, I want to know how, we've got, our starting unit here is going to be 80 miles per hour, and we're gonna convert that into meters per second. We like meters per second in physics because meters and seconds are our standard metric units, miles and hours are not. So we need to start at 80 miles per hour, which instead of mph, I'm going to rewrite in fraction form, miles divided by hours. I'll kind of visually set up the method that I use. And we need to get that transformed all the way over here into meters over seconds instead. We're going to use, this is one that we're going to do pretty often because, you know, on American roads we tend to use miles per hour, and if an example ever gives something in miles per hour, there's a good chance we need it in meters per second before we can use it in any of our equations. So, to start with, we're beginning in miles over hours, and we need to cancel out each of these units to replace them with meters and seconds instead. The question itself lists a conversion factor we can use. We've got 1,609.34 meters in 1 mile. You don't have to memorize any conversions in this class. If one is ever needed, I will make sure you have it, either on the course standard formula sheet that you can use on all your assignments, or I will mention it, make sure it is mentioned in a problem, especially on tests. Again, you don't have to memorize any of these, so make sure you have the conversions. Now, the way we want to use that, again, those two statements are equal to each other. They mean the same thing. So if you turn them into a fraction, one over the other, that fraction is equal to 1. We can freely multiply that fraction by whatever we want. We just have to figure out which unit goes on top or on bottom to cancel out miles and leave us with meters. Our original unit has miles on the top, so we need to make sure that when we write in our fraction, the miles part of it goes on the bottom and the meters part goes on the top, so that the old miles cancels with this and leaves us with meters in the numerator. So this is probably the part of this method that might trip people up the most, is making sure your fraction is stacked correctly. You always want to cancel out the unit you don't want and leave behind the unit you do want. Does that sound all right? All right. And again, you can do this with any unit equivalency. Miles to meters, hours to seconds, inches to kilometers if you needed to. Any equivalency you can use this with. For example, we need to replace hours with seconds. So we have to, since hours is on the bottom, we actually have to put hours in the top of whatever we're multiplying it by to make sure that the hours cancels and leaves us with a different unit of time on the bottom. Now, you're more than welcome to say, do hours to minutes and then minutes to seconds. That would just be 2 links, which is fine. I've been doing this enough to where I myself happen to have memorized that 1 hour is 3,600 seconds, which is just 60 times 60. You don't have to memorize that, but you're gonna do it enough to where you might memorize it accidentally anyway. So, I tend to just jump straight from hours to seconds. You don't have to if you want to. You could do 1 over 60 and then another 1 over 60. But that'll cancel out hours, leave us with seconds. And so now this long, complicated fraction multiplication is what will take us from 80 miles per hour into meters per second. To again show how you would translate this into your calculator, I would type in starting with 80, open parentheses, 1,609.34 over 1, close parentheses, open parentheses again, 1 over 3,600. If you didn't do the 3,600, if you instead did 1 over 60 times 1 over 60, you would write out 1 over 60, close parentheses, 1 over 60. Now this string, if you put it in your calculator and press go, will take us to meters per second. Anyone have a final answer?
I have 35.763.
Very good. So, on average, just kind of for scale, if you are ever converting from miles per hour to meters per second, it's about 40% the size. Like, it means the same thing. If you're going 80 miles per hour, you are moving about 35.5 meters within 1 second, which is pretty quick. And that's how you can use this method for multi-part conversions. Because note here that we turned both miles into meters and at the same time hours into seconds. So you can use this to convert both parts of a unit at once. I also don't typically grade about sig figs in this particular class. I do have some students ask me like where they should cut off a decimal point, just for the sake of mentioning it. Since we started with 80 and all we're doing here is multiplication and one is just, well, since we're starting with 80, we only have 2 significant digits, so the 35 is the significant part. But again, I don't really grade to sig figs, but sometimes if a student asks about it, I'll mention it. How's that one feel? All right. Last one for the day, and I'm mentioning this one because there's a weird catch in it that I want to make sure you're aware of before we have to use it elsewhere. Last up, a rectangular building lot measures 1.00 times 2 feet by 1.50 times 10 to the 2 feet. Determine the area of this lot in square meters as opposed to feet or feet squared. So, actually I suppose there's 2 catches here. First is a review of scientific notation. So, how many feet is this if you were to write it out in a normal number? 100, very good. Scientific notation is just a way of shortening numbers so that you don't have to write out all the zeros. Times 10 squared means that you need to take the decimal point and move it 2 spaces to the right, make it 10 times 10, 100 times bigger. So 1 times 100 is 100. So our rectangular building lot is 100 feet by, what's this one? 150. So you will need scientific notation in this class. Some of the numbers will get kind of crazy big and crazy small. The mass of a planet tends to be crazy big. We will cover electricity in this class. There will be some crazy tiny electrical numbers. So scientific notation is a thing you have to be able to use. But this is our building lot, 100 feet by 150 feet. Now, area of a rectangle is just side by side. So 100 times 150. That's going to be the 100 with the decimal point moved another 2 places. So start the 150. 2 more zeros. So this building lot has a square area of 15,000 square feet. So that feel good? All right. Now, that could have been the end of it, except I do want this in meters squared. So we have to perform one more conversion. I did write in that 1 meter is 3.3 feet. We have the conversion factor, so we can take our feet squared and turn it into meters squared. So I'll just write that out like I did with my other examples. We have feet, we want meters, so we need to take that conversion and put the feet on the bottom to make sure that this foot cancels out with this foot and leaves meters behind. So, are we good to simply take our 15,000 and divide it by 3.3? No. Why?
Squared.
Exactly. Feet squared is not the same as feet. Dividing feet squared by feet doesn't cancel the feet out and leave the squared behind, because feet squared is feet times feet. And if you divide feet times feet by feet, you still have feet. I know I'm saying the word feet a lot. But this operation, if this is all we do, feet squared times meters divided by feet, this feet only cancels the squared. So if this is all you did, your answer would be in feet times meters, which would make Americans and Canadians upset. That's not a thing. So in this case, you actually have to do this twice. You have to add the fraction in, multiply the fraction in twice to cancel out the second foot. And coincidentally, that leaves us with meters times meters, which is meters squared. So the catch here that I want to make sure you're aware of, if you are converting a unit that is squared or cubed, any exponent, you have to factor that in your converting. If something is squared, you have to convert it twice. If something is cubed, you have to convert it 3 times. And we will occasionally have units with squareds and cubes in them. I will briefly tab back to mention that one of our most common units for acceleration has a squared in it. So you need to be aware of this. It will come up often enough that you need to be aware of how to do it. But how do you guys feel for right now? First taste of physics math. All right. Now we're not done with math review. We still have to go over how we're going to use algebra in our formulas. But on Wednesday, we will review that algebra, and then we will start chapter 2 and look at some actual concepts and formulas that will utilize said algebra. Again, no class on Monday, and no lab at all next week because there's no class on Monday. Let me know if you have any questions, needs, concerns, etc., especially if you just joined the course. Oh, one more thing before you go. If you were already registered in the Tuesday or Wednesday lab and you can attend the Monday one, I would ask for you to consider switching so that the wait lists for the older sections can catch up, so we can kind of distribute the course population across all 3 lab days. So please consider doing that before 5 p.m. today, because that's when the add drop function is disabled for the semester. Again, if you have any questions, please let me know. Have a wonderful weekend. Yes.
So EW, that lab would be on.
Come again?
EW.
EW. W is 2 today.
Okay.
The lab lettering goes VWXYZ from Monday through Friday. So W is 2 today, yes.
All right, thank you.
Welcome.
All right, I'm on the golf team, and there's some potential bets I might miss.
All right. That's fine. Did you join the course recently?
Yes, sir.
In that case, I'll go ahead and mention that I don't take lecture
We
attendance.
missed
It's okay if
you.
miss
I know I
days,
missed you guys,
don't
but I'm
have
not
to
even-
explain it, but when you do miss
I'm
one,
not even on
you
campus
should
today, so
catch
I'll
up on
have
whatever
it.
you missed by
So I couldn't
watching
even like stop
lecture
by,
recordings or talking
because I
to
only
class
have class
members.
Monday, Wednesday, Friday.
And let me know if you miss labs, that's the main thing.
Yeah.
All right.
You want to keep this one up?
Yeah,
Yeah, I'll
no,
take
I only
one.
have 2 classes, like 2 extra classes, and I was not about to have like a
Thank you
5-day
both.
week for ceramics. Left me doing it.
Morning.
I don't even like ceramics that much.
Thirsty.
I just like
Stay
you guys,
hydrated.
you know? It was just like a fun class.
Feels all right.
So